السلام عليكم قوتابیانی خۆشەویست. لە دەرسی ڕابردوو باسی مۆمنتەممان کرد گوتمان momentum it is the productive mass and velocity. Momentum it is a vector quantity, it has both magnitude and direction. باسی ئەوشمان کرد گوتمان it is directly proportional to both the mass and velocity کە تاتا ماسەکە و velocity زیاتر بن momentumەکە زیاتر دەبی. و گوتمان directionی momentumiش هەموو جارە it is the same as the direction of the velocity. و باسی ئەوشمان کرد باسی impulseمان کرد گوتمان impulse دەکات ینی کۆژنەکەی دەکاتە force times time دەکاتە چێ دەکاتە change in momentum. ئەو جەگەر ویست فۆرسەکەی ببینەوە یان تایمەکەی ببینیەوە یان change in momentumەکە you make them the subject دوای whatever that is unknown you will find them. So today we'll talk about like it is the continuation با بڵێن تاوکاری دەرسەکەیت کە stopping time and distance depend on the impulse momentum theorem کەواتە ئەو کاتێک کە پێویستە هەتا objectەکە ڕابگیرێتن یان با بڵێن velocityەکەی ببیتە سفر و ئەو کاتێک کە پێویستیتی هەتا ڕابوەستیتن depends on what? Depends on both we can say یان impulse momentum theorem. ئەگەر لەبیت بووبی لە دەرسەکەی دیکە گوتمان we were talking about the impulse equation وەنیە we also wrote this equation gutman force times let's just write this one here. So for example force the net force the change in momentum mass times v final minus v initial divided by delta t whether you need to find the force or the time. If you want to find the time you can rewrite it mass times v final minus v initial لسر force كي باشا. This is how we rearrange the equation أجر ماني force كي ببينه أجر ماني time كي ببينه. This is how we write that. كاتا we can say that both the time باشا for the object to stop it depends on what? It depends on we can say it depends on the impulse momentum theorem here باشا. ما بس ما low equation here. Well also once we find the time we can see actually how long it takes to stop. We can give you a comparison يعني نمونكتان example for example there's a truck that is not loaded يعني هيز ماسا تشيلي يعني بابلين هيز شتا تشيلي بارنكريا it is unloaded and there is a truck that is loaded باشا. We can say that the truck that is loaded if the like how long it takes to stop compared to the one that is unloaded if because obviously it is the same truck and we apply the same force in order to have the same change in momentum so that which is later the it is stopping the truck if they start to slow down from the same velocity until it becomes zero until it stops the truck that is loaded it needs twice as much time as the truck that is unloaded basha. Well, because it needs twice the time we can say the distance that it also travels it is twice the distance for the truck that is unloaded. كاتا دتوانين بابا لتان كنت كينو دتوانين بلين هر كاتك لبرساري باشا داوي أجد داوي stopping time you can use this equation باشا دتوانين بلين stopping time the كاتته stopping time it is equal to stopping time that will be delta t it is equal to mass times v final minus v initial let's set force okay. And also if it talks about the stopping distance we can say delta x or x at this point the 1 over 2 v initial plus v final delta t so عادة قلت v initial final you will be given and of course the question would tell you after you find it here if it's unknown you will have the time then you can find the stopping time. Kata once you find the time here now you can write it here to see how far does the car or the object travel before it completely stops. Basha Kata this is what we have. It's باب قرأنا ليرانا عندك بسال لسرح can see how it is for example how it can be used to solve questions. بس أقول لو studied baby باشا دلين to find the stopping time use the impulse linear momentum theorem أو كاتي أبابلين equation كي rearrange the كي time كي subject which when we say subject يعني by time كلا لا يشبه بتنه دكاتة mass v final minus initial divide by the force here to find the stopping distance أو equation بكاربينه. Now we have a question and بابلين أبساري هل كان see how it is done. It says which is a sample problem 5C. What we have here says a 2240 kilogram, Basha, or 2240 kilogram. That would be the mass, Basha. Let's just write it down. Mass كتسمى 2240 kilogram. Basha says traveling to the west. I got Louis B. When it says west, yani negative, Basha. When it says west, make sure that you write negative for the velocity. It says slows down uniformly from 20, Basha. So from this one, kata with the beta v initial, but because Gutman libere west at the beta negative 20 to this much, kata and the beta v final, but in direction because it is traveling west, kata negative 5 meter per second. It says how long does it take the car to decelerate if the force on the car is this much? Kata force here, how long does it take? But Libi says this force is applied to east, yani later force positive. All right, good man. How long does it take? You can always use this equation. The line delta t the kata mv final minus v initial لسر شيء لسر delta t. زور باش دوباره عفوا لسر force كي باشا. The line delta t it is equal to massa كمان سندليرة. It is 200 يعني بابلين 2240 v final كمان قال لي بابا these are both Gutman west وانيا كاتا لو حالتي هردو شي نيجاتيف بابلين 5 ويان بابلين minus 5 وش minus equation okay دوباره minus or the beta v final v initial is minus 20 as ocean negative got a negative 20 close bracket and then divided by the force which is 8410 newton. So I got load wavy masha or negative the beta positive got the beta negative 5 plus 20 the beta positive 15 times this divide by this and then once you find the time if you do the math you will get 4 seconds basha. Yeah, let's just say 4 seconds. That is how long it takes, let's say, to stop this this car. The second part of a question, let's say, how far does the car travel during the deceleration? Deceleration obviously slow down okay, basha. Acceleration and speed up, deceleration, slow down, basha. How far? Gutman kitale how far yani che yani delta x. Delta x Gutman the kata 1 over 2 v initial plus v final basha times delta t. Bazaga low negative ana beaten of the bubbling of the velocity and bubbling liber direction, okay? V initial kaman Gutman 20 but because it is west, negative 20 plus basha. V final kaman it is negative 5 basha and then times delta t which is 4 seconds. So this negative 20 and negative bubbling plus positive negative the beta negative negative 20 and negative 5 that is negative 25 times 4 that is negative 100 divide by 1 over 2 is going to be 50 it is negative 50 meter basha. If I don't want to write negative 50 meter, what am I supposed to say? We can also say 50 meter but due west basha. Negative here it means, you know, like the same direction as a velocity here. Direction of velocity is west. We can either say negative 50 or it's best to say 50 meter due west. This is how far it travels west. You could just practice them. Force is reduced when the time interval of an impact is increased. Impulse momentum theorem. Subject let's change this color. Yeah, this force, the change in momentum, and v final minus v initial divided by delta time. Is that if this would be the time of impact, right? If this time is larger and longer, then this force, of course, is going to be smaller. What exactly do we use this for? Now, let me give you an example. Let's say here's an egg that drops. If this egg drops on this surface or solid surface here, the moment that this egg hits the ground, later Gutman velocity تواني بلين ليرة velocity كا it is a large it's just a large velocity because it keeps falling and speeds up when yeah. But what happened right after it hits the surface? Now v final ليرة the تواني بلين صفر باشا. You can consider the velocity at this point here. You can call this one v initial, that is before stopping. V final will be 0 because the time of impact بابلين this surface is solid. Time impact okay, like it's really short when yeah. If the time is short اوكاتي قاتا force the impact force اوكاتي will be large. That is why لبرتي the تواني بلين لبروية if an egg falls on a surface and بابلين on a solid ground it breaks instantly. تشكاو فرصة كوالسر يجا كي دبي زوزو جورا دبي لبرتسل تشكا دلين ليرة ماس تامز في فانال لك دبي تصفر مانز في إن شاء الله كجورا كاتا change in momentum كزورا باشا. This time of impact is very short. Again, time ka zor can be nokati. The force of the impact would be very large, and of course, a large force would break the egg. But what if we do the same thing here? This time, if we do that on a, let's say, on a pillow, or it could be on a mattress here. It doesn't matter. When it, let's say this is a pillow here. Asha, this time, if it is going to, could be an air mattress or whatever. It doesn't matter. This egg at the same height, by the way. If it is going to be dropped this time here, the moment that this egg is reaching this this pillow here, this pillow slowly it is going to, for example, where this egg is slowly pushing on the pillow, which the pillow, of course, slowly applies the force on the egg upward slowly until the egg completely, for example, slows down and stops. So V final becomes 0. What does the pillow do to the egg, Baba? What does it do to the egg? The moment that of course, I know you've been on a trampoline. The moment that you're jumping, of course, now you're falling downward. The moment your feet touches the trampoline, do you stop instantly? No. Now the trampoline stretches because you keep moving downward, but at the same time, you slowly until you completely stop, and then now you come back or move up a little bit, and this is how you can safely land the تواني بلين بسلامتي لسه trampoline كده تواني بابلين بإخواري يعني شوته you can go back to the trampoline when yeah kata with this or what this pillow or trampoline does baba for falling objects later so that time impact كي زيادة. What do you mean by time impact later? Like the moment this egg touches the pillow, but ما later طبعا this time is still short, but compared to this one it is way longer. قلت معناها slowly إجاكا دتيت أخواري طبعا أنا بالي فما ترسل هشتك slowly kind of like presses the egg presses on that one yeah حتى بتوابي إجاكا slow down دبي and stop. So this is how I get timey impact زور بيت نوكاتي قلت مان the force يعني the time of the impact زور بيوكاتي force impact okay of course will be less and the egg will not break. This is the base of, for example, a lot of things, Basha. Then you can see that it could be very useful, Basha. So it could be airbag, for example, rescue mattress, could be a lot of other things, Basha. Tamasha, what does airbag do, for example, to protect you? Manha, once, for example, God forbid, if there's an accident, your face slowly would press against the airbag. When it's not like out of the sudden, just like it's the stern. No, slowly presses on the airbag so that your velocity slowly stops, not instantly stops. أوقاتي timey impact كي زيادة بفرصك كم دبيتو and you'll be safe. That is the same thing for this athlete. That's the same thing for this rescue mattress. Could be a lot of other things. Kata no persara wiyan bablin walami persari zor gringabzani. The why it is safer for an egg to land on a pillow rather than on a hard ground. In terms of momentum, time, and force, the egg's momentum will change, Basha. Yan Bablin, the egg's momentum change is the same. Momentum change Bablin final velocity it's the same change in momentum, same mass. And it starts at the same point, it is the same in both cases. But the pillow increases the time of impact. Get time increase get time so the egg will not break it in the case of the pillow. On the other hand, or on the hard ground, the shorter impact time, time impact it is short, Basha. Agar time short bit نوكاتي فرصة كتيلة دبيت a larger force and the egg of course will break. سيدي كشمانية this is the same base you can see here. This is the equation. Kata Twanimblin as a summary or in summary into that we can say impact time gutman get time ka zor biten large bit no kati force kam the bito. So there's no there won't be no significant damage basha. But get time ka short bit no kati the shorter the time impact force ka ziyad the biten basha. Kata Twanimblin get time ka longer be and bubbling longer time spreading the change in velocity over a longer time reduces the force. Kata force ka kam the bi. But time ka short bit increase the force since the momentum change happens more suddenly basha. Kata Twanimblin get time ka short bo kati force ka tilide force ka ziyad the biten and of course there will be more damage in that case. So bash there do pisar walam they know pisari command if the speed of a particle is doubled, how does the momentum change? Equation momentum the mass and velocity. Momentum and velocity it is directly proportional. When if the velocity of the particle is doubled, momentum will also be doubled. And the momentum will be doubled. Later, what happens to it is kinetic energy. But not relation kinetic energy velocity, it is directly proportional to the square of the velocity. Velocity square double the just put that into the equation here. Velocity square double down is 2 square that would be what that would be 4 kinetic energy the beta 4 increases 4 times basha. Here later we can see that it is exactly the same as later do persari di kaman here. And so getting about persara shilo job them walam they know. When a force exerted on an object, does a larger force always result and means a larger change in object's momentum than a smaller force does? Explain your answer. In this equation here, if we go back to the impulse, like if we rearrange that again, force times time, the kata mass times v final minus v initial, we can call this one change in momentum, right? Larger force. Is it always a larger force leads to a larger change in momentum? Force change in momentum like how is that? We'll say Baba change in momentum depends on two things. Depends on force and time. Basha? Even if the force, for example, small, but if the time is large, okati change in momentum will be large. But even watch this, even if the force is large, but if the time is short, like it happens or acts only for a short time, okati change in momentum would be very small. Like how exactly? Take a look. Let me give you an example. This is change in momentum. Change in momentum the force times the time. Force times the time. So that consider the force we have it is 100 Newton, basha, but it only applies or acts for 2 seconds. The change in momentum it is going to be 200 what? 200 we can say Newton second. 200 change in momentum that is going to be kilogram meter per second. What about if we have, for example, on the other side, let's say the force we have is 10. You can see that 10 is way smaller than 100. But what if the time that this 10 Newton is acting is, let's say, is for 30 seconds? Time impact is larger than. In this case, of course, the change in momentum it is going to be 300 kilogram meter per second. Agar blind force leads to a bigger change in momentum, that is not true, basha, because change in momentum depends on both the force and the time. Even a smaller force acting for a larger time can lead or result in a larger change in momentum. Agar force change in momentum the force بس time زور بي أو كاتي change in momentum زياتر دبيتم. No, the change in momentum depends on both force and time. A smaller force acting and bubbling over a longer time can equal بيتين exceed هشتان زياتر بي low force and bubbling low forces دوري it is acting on a short time when over a short time. What is the relation between impulse legal momentum. These two are equal to one another. In impulse the change in momentum. F times delta T the change in momentum. زۆر باش دەتوانین بڵێنەوە سەکشنی یەکەم تەواو. سەکشنی دووەم it is about the law of conservation of linear momentum. هەتا ئێستا کە باسی momentum دەکەن با بە هەموو جارێ باسی یەک ئۆبجێکتی دەکەن. ئەگەر خێراییەکی زیاد کە momentum چی لێ دێ کەم کە momentum چی لێ دێ وانە یان ئەگەر بمانەیە momentumەکەی بگۆڕین چێنجی کەن ئەو کاتی ئەو فۆرسێکا پێویستمان پێیان ئەو کاتە چەندە. We've studied and we've done all that. Now at this point we're going to, let's say, talk about something different. What if we have two objects colliding with one another? Basha? And that, of course, it becomes we can say the law of conservation of linear momentum. Let me give you an example here. So what does the law of conservation of linear momentum says? For example, let's say there are two footballs, Basha. Let's say this is football A and this is football B here. These are, let's say they have the same mass. It could be different mass. That would be fine, Annie. Same mass, Basha. These are same masses. But this one here, initially, it is moving with a velocity. Let's say the velocity of this one, let's say the mass is 2 kilogram. It is 2 kilogram. Basha. This one has a velocity, which is, let's say, 2 meters per second. But this one, velocity of this object, it is 0 before they collide. So what exactly happens after these two collide with one another? You'll notice that after the collision, this ball A that was moving, now it is going to stop. Velocity the beta 0 with the same mass. All that momentum is now, it is going to be converted to the other football here, which is going to make it move, Basha, with the same velocity here. Basha, got that velocity and the velocity of the second object, or object these are, we can say this is before they collide, before, Basha, and this one becomes after the collision, Basha. So after the collision, this one stops completely, hamu momentum convert the B and transfer the B to the second object, which the velocity will be 3. Now, based on this, of course, we can have the law of conservation of momentum, linear momentum. Law conservation of linear momentum, in a closed system. This part is very important, Basha. We can say the total momentum before the impact, the total momentum of the two objects before and after, let's say, will remain the same, constant, Basha. So, what do you mean by in a closed system, Baba? In a closed system, friction heat external force and there should be nothing to make it lose energy. Basha? Anything that could affect these two and these objects we're talking about disregarded, ignored. Basha? Friction, radiation, so we assume that no energy is lost. Basha? We can say that in a closed system, the law of conservation of linear momentum, in a closed system, the momentum of the two objects, Basha, for an isolated system, closed system, the total momentum of all objects interacting with one another remain constant regardless of, let's say, the type or the nature of the collision and the forces, let's say, the nature of the forces between them. What we said, we can write this as a mathematical equation. We can write it this way, Basha, the law of conservation of momentum, sigma p, this sigma means the sum of, Basha, the sum of momentum before, it is equal to the sum of momentum after, Basha. But we're talking about if we have two objects, what is the momentum of the two objects before the collision? We can say that, Basha, so let's just rewrite this one here. The sum of momentum, we can say before, Basha, the collision, it is equal to the sum of momentum after the collision, Basha. So if we're talking about two objects, of course, like we said it earlier, Basha, so here it becomes, this one stops, the other one moves, right? This is what we said, if each one of these has a momentum. So we can say M1, Basha, V1, but these are before the collision, Basha. When we say before the collision, we can write initial instead, Basha, plus M2, V2, but these are initial. If not, you could just write one big bracket and write initial, that is before the collision here. All right, but since we already wrote it, it doesn't matter. Like this equals to Basha, according to the equation here, the cat M1 V1, but this time this is after the collision, so you can call that V final, Basha. And then plus M2 V2, again, final velocity of the second object here. So these two sides must always be equal whenever we study the momentum of two or even more objects. So object ثاني كواحد معناته we have two objects, so this is what you need to know, Basha. So this is what the law of conservation of momentum is. But just be aware of the change in the direction, all right, of the velocity after the collision. I get direction velocity can reverse bu. I got maybe direction motion okay also will be reversed. Yan bawlin awkati tabi the equation is reverse ikeo. The linear momentum is conserved for objects pushing away each other. So now this two person here, Masha, let me explain this one. What is the velocity of these two person, for example, this two-person brother and sister playing ice, let's say ice skates. But now this is, of course, both are stationary. This one has a certain mass. The brother and the sister also has a certain mass too. Mass 1 for the boy, mass 2 for the girl. So their velocity here, V1 initial is 0, V2 initial is also 0. But after they push each other away, I need you to focus on this one here. You can see that these are how they're going. This is, we can say mass 1, again mass 2, but look at their velocity here. So this is going to be velocity for, right, for person 1, but it's going to be final. It was 0. But if you look at the direction of motion, this is to the left, and so this one becomes negative. This one here, it is to the right, V2 final, because it is to the right, so it is going to be positive. So we can say momentum before the collision must equal to momentum after the collision, and you can see that what it is written here. The total momentum before 0, the total momentum after the collision must also equal to 0. And that is, you can get it. Now, let's solve the question and see how it is done, Basha. Starting with this one here. The question that we have, Basha says a 76 kilogram boater, Basha. Boater, that would be the person, Basha. The person who's going to, let's say, get on a boat or ride a boat, if that is correct, Basha. So, Gutman, 75 kilogram boater. But before we do this, it's very important to make a table exactly what we've done here. So now, clearly, we have two objects. One of them is the boater, would be the person, Basha, and the other one is going to be the boat, Basha. So this person is going to jump on this. Now, because we're talking about mass and velocity and all that, so it is important to mention each one of them, Basha. So we can say mass of the boater, that would be the person, V initial for the boater, and then we can also say V final too, right? For the boater, we could do the same thing. That'll be the mass of the boat. You can call that M2 or object 2 here. And then V initial for the boat, right? So these are V1 initial, you could say, V1 final. This for the second object, so V2 initial, V2 final, this would be for the boat. So this is the table you need to make, Basha. Now, all you have to do, just now table like whatever that is unknown, you can find that. So for example, how do you fill it now? It says a 76 kilogram boater, so that would be the mass of the boater, the person, 76 kilogram, Basha. It says initially at rest, Basha. Initially at rest, and V initially person gets in that 0. It says in a stationary 45 kilogram boat. Kata massi boat gets in that 45 kilogram boat. And also says stationary boat. Kata velocity boat gets in initially. It is also 0, Basha. 0 meter per second, 0 meter per second. Let's say at Beirut Harbor, steps out of the boat and onto the dock with a velocity of this much. Who's stepping out of the boat? Obviously, the boater with a velocity of this much. Yani this is V final, right? So V final, it is 2.5 meter per second, but I got the direction KB to the right one, yeah? So to the right, that would be positive meter per second. If this person is moving and bubbling, jumping to the right, obviously, let's say this is the boat in here, Masha. So here's the dock or whatever. If this person is jumping, maybe too much tilted. If this person is jumping to the right, should be on the other side here. If this person is jumping to the right, the boat must move to the left. What is the final velocity of the boat? Final velocity boat. Okay, but we know. Now let's solve this one together. Now we can say, whenever it gets to questions like this, because we have two objects, so we can say the momentum before the collision must equal to momentum after the collision. After this. What is the momentum before the collision? We'll say m1 v1 initial plus m2 v2 initial. It is equal to m1 v1 final plus m2 v2 final. Good man. Here, so clearly the velocity of the person initially is 0. Yani O parte hamui will be 0. What about the velocity of the boat? That is also 0. The whole thing, this side is 0. Now, what about this one here? Good man. M1, what is M1 by the way? It is 76 times V1 final is that we have it, which is 2.5. Plus, what is M2? It is 45 times the V final, and V2 final, and this is the one that is unknown we're trying to find. This is obviously 76 times 2.5. We could just write it here. Let's get a calculator and see what is it equal to. So we can say 76 times 2.5. 76 times 2.5. It is equal to 190. So we can say, and you can move this 190 to the other side, it becomes negative 190. So just move that to the other side now. It is equal to what? It is equal to 45 times V2 final, which is going to be V of the boat. So how do you find V2 final? Both sides divide by 45. 45, these two cancel out. We can say V2 final, the 190 divided by 45. The answer is going to be 4.22, and it's negative. We can say V2 final, the negative 4.22 meter per second. And what does this negative mean? That means it is due to the left, or if not, you could just say V2 final, the 4.22 meter per second to the right, to the left. Now that's it. But if he's jumping to the right, the boat kind of like moves under his feet to the left. This is what it is. بساركان تواني بلن زور آسانة تنها لتزيدها بنيو equation كي بنوسو لتزيدها بنيو اشتتشوا نامينكم أو بسارش مانية بسارش جوانا فكرتش تذا بيم خوشلوت حالكم. What does it say? A 63 kilogram astronaut. So this is the astronaut. Okay, so what is his mass? So we have an astronaut. His mass is 63 kilogram. That is the mass. It is on a spacewalk when the rope line to the shuttle break. Oh, this habal grease, whatever that you call that, the one that kind of like attaches him or ties him to the shuttle, it just breaks. Bablin break debited. So the astronaut is able to throw, the astronaut is able to throw a 10 kilogram oxygen tank in the direction away from the shuttle. I need you to focus on this one a little bit. So the mass of the second object that we have, it is the oxygen tank. The mass is 10 kilogram. And if you look at this one here, it says this oxygen tank, it is directed, Bablin, it is throwing the oxygen tank away from the shuttle bus. But before we do this now, is in this oxygen tank with the astronaut first, what is the velocity of the astronaut before throwing this one? It is 0, right? We can say V1, because these are both, it's almost like you and your backpack. Once you're holding your backpack, it is with you, right? If you're not moving, your velocity is 0. Velocity backpack it is also 0. So imagine this oxygen tank, it is like a backpack. V1 initial for the astronaut is 0. But what about the velocity of the oxygen tank? That is also 0. Let's say this is the oxygen tank. Why? Because it is in his hand. اگر بخوي نزوليتن كاتا يعني بابلين velocity خوي صفر بيتن velocity oxygen tank كش initially is 0 كاتا V2 initial is 0. We can say these are both 0. But then after that, you can see that it says the oxygen tank in a direction, so he's going to throw it now. Basha? But a direction here, if he's going to throw it away, all right, this is how the oxygen tank is thrown now. Of course, he's going to move backward. If you're on a skate, if you throw your backpack away, you'll be moving backward. Back to Chanda, back to the space shuttle, you could say. So Kawata, in this case, if he's throwing the oxygen tank away, that'll be away from this, right? So it is going to be positive. With what velocity? It says with a speed of 12 kata, we can say V2 final for the oxygen tank, it is going to be 12 meter per second, propelling the astronaut back to the shuttle. Back to the shuttle, يعني backward وكاتي V2 final the astronaut okay دبيت تسنبابة دبيت negative لبرسه says back to the shuttle يعني backward or negative. Assuming that the astronaut starts from rest, بخوي بدل find the final speed of the astronaut كاتا V final كمان سنده. اللي بس ما كنت معنا غير astronaut if it is at rest oxygen tank كش at rest. But after you throw the oxygen tank forward, you go backward. كاتا دبي V final the astronaut negative درسي negative درنا وكاتي غلطة. زور باش. So now all you have to do just plug in the numbers now. Okay, زور باش. كاتا 20 بلين M1 V1 initial plus M2 V2 initial. The كاتا that is the rule, right? M1 V1 final plus M2 V2 final. Now all you have to do is just plug in the numbers. قلت معنا وانا بدايتك هرديشان صفر كاتا these two part is 0, so 0 plus 0 that would be 0. Later, what is M1 V1? قلت معنا that would be mass of astronaut 63 times V1, or we can say V1 final, which we don't know when that would be the velocity of the astronaut plus قلت معنا data mass oxygen tank كاتنا velocity because it is forward, it is going to be what? It's going to be 12. So now all you have to do is just do the math. 10 times 12, that is 120. So we can say and move this 120 to the other side, becomes negative 120. The kata 63 times V1 final. Kata, now you could divide both sides by 63. 63. When you kata, you can see that it's negative now. When you beat the V1 final, which is the velocity of the astronaut, it's going to be negative what? It is negative 1.9 meter per second. Negative it means back to the shuttle bash. So you could say 1.9, you could also, if you wanted, say 1.9 meter per second backward. Basha, and back to the shuttle. Doesn't matter. Basha. This is the final velocity. There is nothing much left. أو يديك اشتشينوي تدانية وقلت ما قرنترين اشتيجليرة أم حالو كتيب لكيبكا ما سوفلوستي كان بنوسا أو يديك unknown go find it. سيدي كشماني Newton's third law leads to the conservation of linear momentum. طبعا Newton's third law we can say simply for every action there is an equal and opposite reaction. When the pasha homai the twani blend, the change of momentum of the two objects will always be equal and opposite. Kat the twani blend change in momentum object yakam, it is always equal to the change in momentum of the second object, but it's always in opposite direction. Kat the twani o equation ebunu say again o equation is okay. For example, if you simplify that on or if you write the whole thing, then you'll get the same exact equation that we've mentioned before. Kata, the only thing you need to know is this one right here and nothing more than that. Concept Babla, in another topic, it says force and rail collisions are not constant. What exactly do you mean, Baba? Sometimes when we talk about forces, when you apply force on something, the momentum change. But like this force that you're applying, like are you applying this force to the object? Is it the moment that you touch the object or you apply the force until you, let's say, move away from the object? During or while you were applying the force, look at to force object are you applying the same force? Of course not. Kata, in real collision, the force is different. How about example like it? The moment that you jump on a trampoline, the moment that you fall on a trampoline, the moment that your feet touches the trampoline, that is a very small amount of force that you're applying on a trampoline. But then the more you fall further, of course, the trampoline stretches more and more and more. And we can use this diagram for that. Consider you falling on a trampoline. That is you falling here. The moment that your feet touches the trampoline, this is what happened. The more you fall, let's say fall down further, the trampoline stretches here beneath your feet. Becomes maximum. That is where the trampoline stretches the most, we can say. And then after that, you're about to, for example, to be pushed upward. This force that the trampoline applies on your feet, now at this point here, it is going to decrease more and more and more until you leave the trampoline. That is when you jump upward here at this point. So of course, now this will be the action and reaction force, you can call that. So this will be the force you apply on the trampoline. On the same side, the trampoline would be applying a force on you. So for every action, there is an equal and opposite reaction. But this is normally how it looks like. You can say, what is important here, in real collisions, forces are not constant, but vary, change over time. The forces are always equal in Babylon. The forces are always equal in opposite, but their magnitude change during the collision. These are more questions of what you solved before. Now let's talk about section 5.3, that is elastic and inelastic collision. So the type of collision, when objects collide, there are three types of collision now. We have perfectly inelastic, we have inelastic, and then there is, we can say, elastic collision. Perfectly inelastic, there is inelastic, that is the second type. Third type is elastic collision. What are the difference between each one of these types of collision? In perfectly inelastic collision, after the objects collide, they stick together and energy is always lost. But momentum is always conserved. Momentum before the collision, it is equal to after the collision for every kind of collision. That is non-negotiable. No discussion about that. The second type of collision we have, it is just inelastic. In this type, momentum is conserved. The two objects collide, they separate. But energy or kinetic energy still will be lost. The third type of collision that we have, it is called elastic. The objects collide and then rebound. They separate, but obviously the momentum is conserved, but kinetic energy is not lost, or we can say kinetic energy is conserved, and that is the only type of collision where kinetic energy is conserved. Kinetic energy lost تبي بس momentum لهر سه type of collision it is we can say momentum is conserved. Perfectly inelastic objects stick together. Objects stick together and energy is lost, or you can say kinetic energy is lost, it doesn't matter, or you could just say kinetic energy lost and is lost. Later, objects separate, kinetic energy do better, it is lost. Later, objects bounce perfectly, and you can say kinetic energy is also conserved. But for all of these, momentum is always conserved. Because the first type of collision that we have, of course, an example for that would be car accident moving together after the impact. So what exactly do we do here? The two masses stick together. If two objects are moving together, we combine their masses. There are two objects here that they collide. You can see that these are before the collision, objecti يكم objecti دوم باشا, but after the collision, they stick together and then they move with a certain velocity. Because they stick together, كواتا, we will add their masses and then we'll just say mass 1 plus 2 times v final, because now after the collision they both travel and move with the same velocity. So this velocity will be for both. Basha, yan the same for both. Kata equation katsili de m1 v1 initial basha plus m2 v2 initial the beta m1 plus 2 لبرسة قتمان because they stick together times v final. ما بسارة لسه حلقة. أو example man here. Our example says a 1,850 kilogram big car, Basha, so like a truck maybe. So what is the mass of a car? By the way, don't forget to make the table, Basha. So table like here, we'll just keep the table. It's about table like dibarana keno. عندك قارب كنيرة. And I think we'll just move this one up a little. زور باش. دير بساركة. Let's just zoom out. زور باش. دير بساركة, as you can see here, the question says there is 1,800 kilogram big car, Basha, so we can call this one car 1 if you want to. Massa it is 1,850 kilogram. So stopped at a traffic, Basha, kata V initial V initial is 0. And then traffic light says struck from a rear, Basha, rear and إلى دواوة سارش ديك خويليدا. Babylon struck from the rear by a compact car. Compact later ما بس سارش كتير باشا with a massive kata massi sari دوم تندا. It is 975 kilogram. The two cars become entangled. Entangled يعني they stick together, Basha. So you can write it here. Stick together, Basha, or become one as a result of the collision. If the compact car was moving, so it says compact car, يعني ما بستيجي بابا, the second car was moving at a velocity of was moving, and this is the initial velocity, 22 meter per second, but to the north. كدل north, that is positive. Wrya, before the collision, what is the velocity of the entangled mass after the collision? In other words, you can say, what is the velocity of the two cars after the collision? equation because they stick together. M1 V1 initial plus M2 V2 initial. The kata, because they stick together, M1 plus M2 V final. The truck and the car 1, the big car was stopped, so this part is 0. Basha? Now if this part is 0 and the whole thing is 0, plus, so we can say 0 plus masi duam tanda 975 times Gutman V initial was 22, that is for car number 2, that is equal to masi akam, it is 1,850 plus masi duam, it is 975. 975, and then times V final, which is unknown here. Now all you have to do, just do the math and you can find the final. Basha, or we combine kebaba. So both sides, by whatever the result is, you have to divide both sides, and then you can find V final. Kata V final, the katasan, that is equal to 7.6 meter per second. And because it is positive, kawata, it means still the same direction as the two cars, Yambabla and the compact car, Basha, or you could say due north. Later, this is the big car here. That is, so let's do it here. Big car waiting at a traffic light, Basha. And then you can see that it was, and then there is another car that hits this one, which is moving to the north. And then after the collision, these two stick together and then they both move together. Of course, because this one was moving north, the velocity of the two, or the direction of the velocity of the two, will also be north. Gutman velocity كده كانت 7.6 meter per second. Oh, that's easy. There's nothing, like difficult regarding this one. I would like to solve this question as well. Says a 1,500 car traveling 15 meter to the south, أقل south beaten, which means negative, collides with a 4,500 kilogram truck that initially at west. So let's write the information that is given here. The first car is 1,500 kilogram. All right, then it says 15, or the initial velocity is 15 meter per second. It says to the south, so negative, collides with another car. The second car's mass is 4,500 kilogram. That is initially at west. When it says at west, that means initial velocity 0. The truck or the car and the truck stick together, and they become one, and move together after the collision. What is the final velocity of the two vehicle mass, So at this point here, all you have to do is just write the equation on that. It'll be at Gutman M1 V1 initial, M1 V1 initial plus M2 V2 initial. It is equal to M1 plus M2. These are all V final. So as you can see here, it says M1, it is what? It is 1,500. That is 1,500 kilogram, 1,500 times Gutman V initial, that is negative 15, right? Plus Gutman, because V2 is 0, so this part is going to be 0 here. That is going to be M1, which is 1,500, plus M2, which is 4,500 times V final. Now all you have to do is just find whatever it is and then divide both sides by that number here. And then you can, of course, this two will cancel out. Then you can find V final. V final, you can see because there's a negative there, so it's going to be negative what? It's going to be negative 3.75 times, or you can say meter per second. And this negative, or if you can rewrite this one, you could say 3.75 meter per second due south. Because this negative means south. So if you ignore, or if you don't write the negative, you have to say due south. All right, that'll be the end for this session. Inshallah, there will be more videos like this. So keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.